Arizona Biosphere 2. And on behalf of the University of Arizona College of Science, I would like to welcome you to tonight's Saddlebrook Science Cafe lecture. It's about time. It's going to be fascinating. Before we get to tonight's speaker, I have just a few announcements, little housekeeping things I'd like to go over with everyone. The first is if you could please turn off or silence your cell phones, just so that we don't interrupt our speaker. I double-checked mine a minute ago. I was actually embarrassed once with my phone ringing as I made these announcements. So has not happened since then, I can promise you. Tom and I will both do our best to speak clearly right into the microphone tonight so everyone can hear. So, but if at any point you're having trouble, please raise your hand and that'll be a reminder to both of us to bring up our volume. One thing I wanted to mention, you may have noticed on the table when you were coming in, we have an evaluation form about tonight's program. If you have a few minutes on the way out, we'd really appreciate your feedback. It helps us know the kinds of talks the community is interested in, how we can continue to improve these and make this a great Science Cafe lecture series for you all. So I will stick around until every last eval is filled out. This is the last talk in the fall, and then there will be 4 more in this series beginning in the spring. Another piece of material we had out, the next talk is called Geologic Time. There's a flyer out on that table if you'd like to pick that up. That'll be January 14th, again, 6:30 p.m. right here in the theater. We also, you'll find a trifold brochure that lists not only the remaining talks in this series, but all of the other Science Cafe lecture series around town. So if you like these kinds of things, there are many more to check out around Tucson. You may have noticed as you came in behind me, the slideshow was sort of scrolling through some of the College of Science outreach venues. Places like Biosphere 2, the Flandreau Science Center and Planetarium down on main campus, the Laboratory for Tree Ring Research. All of these are fascinating to visit. Many of them have tours, exhibits. So all of them, we have flyers and materials about these venues out on the table. So perhaps if you have family coming in for the holidays, grandkids, there's some fun and interesting science-oriented activities to do at these different venues down on the main campus, or in my case, Biosphere 2, just a little bit north of your community, or the Mount Lemmon Sky Center, which of course is up on Mount Lemmon. Some of you, as you came in, and I think Tom said he brought 150, were able to pick up what looked like a little calculator, a clicker. This is going to allow you to participate as audience members during tonight's talk. Some of you I know didn't get them. Perhaps if you could share one as a couple, that might give your seatmates around you who didn't get one, you might be able to share a little bit that way. So feel free as a community to help each other out. And Tom's going to give you a little bit more information about how those will work this evening. And then, of course, Tom is going to speak for about 45 to 50 minutes. And if you're not familiar with this format, we always allow time for questions and answers. So it's not as easy for me to circulate among you with the microphone. I'll go on the perimeter. If you want to get up and belt out a question, that's fine. Tom or I will repeat the question into the microphone so that everyone can hear what's been asked. And then you'll, of course, get an answer to that question. So looking forward to that. Yes, sir. Yes, in fact, the question was, this is a good little segue here, we are going to bring the house lights down about halfway to make it easier for you to see the screen, but leave just enough light so that if you need to go out and use the restroom or something, it won't be so dark that you can't see where you're going. So we will definitely do that. So now, without further ado, let me introduce tonight's speaker. I'm very pleased to introduce Dr. Thomas Fleming. Dr. Fleming is an astronomer and a senior lecturer at Stewart Observatory down at the University of Arizona. Tom obtained his bachelor's degree in physics from Cornell University and his PhD in astronomy from the University of Arizona. He coordinates the general education program and the public evening lecture series at Stewart Observatory and sits on the university's general education committee. His research interests include X-ray emissions from stars and teaching astronomy to students not majoring in science. Tom is responsible for turning the Flandreau Planetarium Theater into a functioning classroom. He loves to sing and is a founding member of the Arizona Repertory Singers, who have performed here at the Saddlebrook DesertView Performing Arts Center in the past. Tonight, Tom will treat you to a lesson on the history of our universe from its inception to the creation of our Earth, taking note of the timescales involved. Please join me in welcoming Dr. Tom Fleming.
Thank you very much, Matt. Thank you very much. So, there we go. It's a pleasure to be back here. I think I gave a lecture here back in October of 2014. But this year, the lectures have a theme, and that is time. And before we continue, I also want to make a shameless plug because I host the Stewart Observatory Public Evening Lecture Series. During the school year, every other Monday night, we have a public lecture at Stewart Observatory down on the campus with telescope observing at the historic Stewart Observatory. We've been doing this every year since September of 1922. Yeah, and that was long before the College of Science even existed, okay? So we've been doing this a long time because the people of Tucson have always been interested in astronomy. The other thing that I'm very proud of is that the college asked me about 3 years ago when we reopened the Flandreau, I still call it the Flandreau Planetarium, okay? Because when I was a student here in the 80s, it was the Flandreau Planetarium. But now it's a science center. Okay, fine, but it's a planetarium. And when it reopened, they asked me if I would turn the planetarium theater into a classroom. And I have loved it. I've been teaching in Centennial Hall, okay, to 600 students. And I love the intimate atmosphere, 135 seats, though after next summer, it'll go up to about 160 seats when we take the old projector out. But we have a brand new digital planetarium system. If you haven't been to campus to see the Flandreau Science Center and Planetarium, you gotta go there. And that's my classroom. My students twice a week for 16 weeks, I have the sky above them and I can simulate anything in the universe to teach them. And one of the things I use are the clickers. Now, you have a very old clicker that we used about 10 years ago. And, but I was able to pick them up on the cheap, all right? And I bring them to elementary schools too. The little, 6 and 7-year-olds really like them. And this is what I'm gonna do. I mean, I'm a one-trick pony, okay? I'm gonna teach you the way I teach my 18 and 19-year-olds, okay? And this is how I do it, so pay attention. You heard from Pierre Maestre last month, those of you who were here, about the concept of time. And now we're going to drill into the different ways that the different disciplines at the College of Science see time. You're going to hear the astronomical view tonight. In January, you'll hear from my good friend Jessica Kapp about the geological view, and you'll hear the biological view and the psychological view. So some really neat things ahead if you can come to all of these lectures. I'm talking about cosmological time. You're going to realize what this is that we're seeing. But I always like quotes. I love quotes. The textbook I use has quotes at the beginning of every chapter. Here's a quote from one of my old professors at Cornell University. Somewhere, something incredible is waiting to be known. That's right, that was Carl Sagan. So, let's start with the historical perspective, the Great Debate. That's what we call it in astronomy. It happened on April the 26th in the year 1920. And it occurred just 2 years before we started giving public lectures at Stewart Observatory. The Smithsonian Museum of Natural History, Baird Hall, is where it took place. It was sponsored by the National Academy of Sciences. The topic was the scale of the universe. A young graduate student in 1915 named Harlow Shapley had just proven in his PhD thesis that the sun was not the center of the universe. The history of astronomy is the history of knowing that we're not important. For many centuries, we thought the Earth was the center of the universe, and everything in the sky just rotated around the Earth. Then after he died, Copernicus published a book that said, well, no, the sun's at the center, and we orbit it. And Kepler said the same thing, so did Galileo. He got in trouble, okay? But after all the growing pains of this, eventually everyone sort of agreed, okay, yeah, the Earth isn't the center of the universe. We're a planet just like the other planets, but our sun is the center of the universe. And that was the overall view in the 18th and 19th centuries. Beginning of the 20th century, though, Harlow Shapley was starting to tell us that, you know, I've been measuring these things called globular clusters, and they aren't centered around the Earth. They're centered around some position way out there in the direction of Sagittarius. So this was a big topic for debate because people were starting to realize that, okay, the sun's not the center of the galaxy, but certainly our Milky Way galaxy is the universe. And that was the issue. That was the great debate. What was the scale of the universe? What was the nature of the universe? So two eminent astronomers, young Harlow Shapley, who was 5 years past his PhD. Harlow Shapley was from SoCal. He did his work at the Mount Wilson Observatory outside of Pasadena, California. Hebert Curtis was from the Lick Observatory. So there was also some, you know, that's up Mount Hamilton and NoCal. And it was NoCal versus SoCal, but it was a big debate. And here's the urban myth, because I know Pierre told you about Einstein's view on time. Now, it's been said, there are people that secondhand references, it's an urban myth. We don't know for sure, but possibly Albert Einstein himself was in the audience there on April 26, 1920. So here were the positions. Harlow Shapley, he's the man who dethroned the sun. The sun is not the center of the universe. He used a type of technique using RR Lyrae stars to measure the distances to the globular clusters. And he showed that not only was the sun not at the center of the Milky Way galaxy, the galaxy was a lot larger than we had thought. He claimed the galaxy was 300,000 light years in diameter. Now, it turns out he got that wrong. It turns out it's about 100,000 light years. And that's because he didn't know about the interstellar medium. At that time, there's actually gas and dust between the stars in our galaxy. They didn't know about that. So he would think that a globular cluster was faint because it was far away, when really it was faint because there's dust in front of it. So you would overestimate your distances. But still, up until then, astronomers thought the Milky Way was only about, you know, what, 30,000 light years across, and the sun was at the center. He also, though, thought there were these beautiful, when they started taking pictures with cameras and telescopes, these beautiful little spirally things, and they were called the spiral nebulae. He thought that the spiral nebulae were nebulae within our galaxy. So Shapley's view was, okay, the sun isn't in any important place in the center of the universe, but our galaxy is. Our galaxy is the universe. His opponent was Hebert Curtis. He said that the sun was near the center of the galaxy. That's what he had thought until he was convinced that that was not true. But he maintained that we had a small galaxy, only 30,000 light years across. That was the number given by a Dutch astronomer in the late 1800s named Kapteyn. But here's what Hebert Curtis said. The spiral nebulae were island universes. That's the term he used. He said that the Milky Way galaxy is not the universe, not everything that exists. It's one of many galaxies. And that these little spiral nebulae are actually island universes. There are other galaxies, and we are one of many. The universe is made up of many galaxies. And this was the big issue that astronomers argued about in 1920. Is the Milky Way all there is, and very large, or is it relatively small and one of many galaxies? And he was wrong about the size of the galaxy. Well, it turns out, just like in any debate, Curtis was right about some things and wrong about other things. Shapley was right about one thing, wrong about another. Shapley's points that the sun is not the center of the galaxy, he was right about that. He claimed the galaxy was larger than was thought at the time, and he was right about that. Turns out he was wrong in thinking that the galaxy was the entire universe. He thought the spiral nebulae were actually nebulae, but they aren't. They are conglomerations of hundreds of billions of stars and nebulae that are very far away. Now, this guy is the guy that we'll get to him in a moment. The one thing, though, about this debate that's interesting, of course, Shapley lived until 1972. He's director of Harvard College Observatory. And Shapley, well, here's what happened, okay? Edwin Hubble came along just 5 years later and showed that the Milky Way galaxy, the Andromeda galaxy, was 2.2 million light years away from the Milky Way galaxy, from the Earth. So there's no way the Andromeda galaxy, the Andromeda spiral nebulae, could be inside the Milky Way. There's no way. And so pretty much Shapley's idea was shot out of the water 5 years after the Great Debate. And that's what people remember. But eyewitness accounts and recounts and stories about the debate thought that actually Shapley had won it, and Shapley thought he won it because he claimed that remember what the title of the debate was. The title of the debate was the scale of the universe, or in this case, the scale of the Milky Way galaxy. He was right about that. Curtis was wrong. Milky Way is a lot bigger than they thought it was. And he kind of accused Curtis of hijacking the debate and saying that, yeah, but he started making a big deal about these spiral galaxies, these spiral nebulae. Turns out that Shapley was wrong about that, but even though that's not what the topic of the debate was supposed to be about, that's what people remembered. And so Shapley historically has always been seen as having lost that debate. But you can see what's going on here in 1920 is that astronomers are thinking about the universe as a whole. What is the universe? How big is it? Now, of course, this gentleman is the one that solved or basically put an end to that particular debate because he discovered Cepheid variable stars in the Andromeda galaxy. And therefore, he was able to measure the distance to the Andromeda galaxy. He estimated a distance of 2 million light years. It's about 2.2 million light years to the Andromeda galaxy. That's far away. That's farther than anything in the Milky Way. So this is a different galaxy. This is not part of the Milky Way. We also know Edwin Hubble because he developed a classification scheme for galaxies. He took lots of pictures of galaxies, and like any good scientist, you know, when you capture a lot of butterflies, you start to classify them based on the sizes and shapes and colors of their wings. He did it with galaxies. Based on their shapes and sizes, he developed a classification system that we still use to this very day. I mentioned Cepheid variables. I want to show you how a Cepheid variable works. Unlike the rest of our colleagues in the College of Science, we don't have a laboratory because we can't touch the things we're studying. We can't run an experiment over and over again and change the variables because the things we're studying are millions and miles and light years away and millions of light years away. All we can do is watch. But fortunately, if we watch long enough, we'll notice certain things in nature that we can use to our advantage, like the Cepheid variable. Cepheids, named after the first star of this type that was studied, the star Delta Cephei in the constellation Cephus, or Cephus the king, a husband of Cassiopeia, they're giant stars. But these giant stars pulsate. Their radii actually increase and decrease. And when they do that, as you can see, their surface area increases. When the surface area increases, the star is brighter. It's more luminous. It emits more watts. When it decreases, the surface area gets lower and it gets faint. This is what astronomers call a light curve. A light curve is when you observe a star, for example, and just observe the hell out of it over and over and over again, every half hour, hour after hour, night after night, month after month, year after year. And what you plot is time versus the apparent brightness of the star. How bright does it appear on your photograph? Now, a star that is perfectly constant in its luminosity, in its wattage, its light curve will be very boring. It'll be a horizontal line. But notice these stars get faint, then bright, then faint, then bright. And notice that they get brighter faster than they get fainter. So the light curve goes up fast, down slow, up fast, down slow. This is what's known as a sawtooth curve because the shape of the light curve looks like the teeth of a saw. And the other interesting thing that astronomers, especially a famous astronomer named Henrietta Leavitt, noticed was that if you look at each maximum point, the point when the star is brightest, until the next time it's the brightest, till the next time it's the brightest, it's always the same. It's a regular periodicity. And what they did is they observed many, many of these stars, and what they found is that some of them pulse really quickly, and others, like here's one, you see what you would do is you would measure what's that date and time, what's that date and time, what's the difference? Some of these pulsed every day, every Earth day. Some took 10 days, some took 30 days. But if you then figure out how far away these stars are and measure the average luminosity, for example, here's an example of another light curve. Notice how this light curve is much longer. It's a slower pulsator. Turns out the stars with the longer periods have the brighter average brightnesses. Think of it this way. A smaller Cepheid star is going to have, on average, a smaller surface area. It won't be as luminous, so it can pulse faster. It has the shorter period. A bigger one that's brighter and more luminous has more mass to move around, so it pulses more slowly, has the longer period. This is what we call in astronomy a standard candle. A standard candle, it's like I can put two lights in front of you and they can look identical. Then I lift the curtain and show you that one is a candle flame and the other is a lighthouse beacon. How can that be? How can a lighthouse beacon be the same brightness as a candle flame? If the lighthouse is 3 miles away, right, and you're looking at it through a window and the candle is on a table right in front of you, that can be the case. Well, a standard candle is any astronomical object whose luminosity, whose true brightness can be calculated without knowing its distance. In the case of the Cepheids, I just have to measure how often these pulses go. What's the time between the two maximum brightening periods? Then I know its true luminosity. I can compare it to how bright it appears from Earth, and it's a simple matter to calculate the distance. So that's how he did it. And I have a little flow chart showing you how this technique works. I tell my students, for the students in the Eller College of Business, this is for them, because the business students like flow charts. You measure the period of the Cepheid's light curve. It yields, via this relationship between period and luminosity, its absolute luminosity. You combine that with its apparent luminosity, and what it yields is the distance to the star. Because it turns out light traveling through the universe follows a very simple inverse square law. Double the distance, your star gets 4 times fainter, right? Triple the distance, 3 squared is 9. The star gets 9 times fainter. So as long as I know how bright it appears from Earth and what its true luminosity in watts are, I can calculate how far away it is. And that's how Edwin Hubble was able to measure the distances to these galaxies. Got your clickers ready? Here's your first chance to see if you've been paying attention and if you can now synthesize the information I've given you to answer a question. Cepheid variable stars are discovered in 2 different galaxies. We'll call them Galaxy A and Galaxy B. Both stars have the same average apparent magnitude. So when I take a picture of both galaxies, the stars appear the same brightness as seen from Earth. The star in Galaxy A has a pulsation period of 10 days. I need to move this. I'm sorry, this is in the way. And the star in Galaxy B has a pulsation period of 30 days. Which galaxy is at a greater distance from us? Is the answer A, B, C, or D? Notice we're getting answers right now. They're coming in. And I think I can, I start a timer. I have a 40. Something weird happened to my timer. That's 40, but the 4 is above the 0. Now again, you're not supposed to talk to each other. You'll get a chance to do that. I want every one of you that has a clicker. If you're sharing a clicker, then talk to your partner. But I want you to answer the question, which galaxy is farther away? This number should get up to 150 because I brought 150 clickers. And by the way, I turned on the anonymous button, so I don't even know the code of your clicker. In class, I know the code of my students' clicker, so I can see what every student. Okay, now this is how the technique works. Polling is now closed. What I now do is hide this from you. And I look at the results. 70% of you got it right. Wow. 70% of you got it right. But just to show you, usually in class, I think I'd still make you discuss it though. So here's what I do. I move on to the next slide, which guess what, is identical to the last slide. So you can see the question. I want you to discuss it. Now realize 70% of you got it right the first time. But talk to the people around you. Ask them what they answered. If you're confident that you are correct, then try to convince the person next to you, if they answer differently, to change their mind. Explain to them why they're wrong and you're right, okay? And if you were just guessing, maybe you can learn something from the people around you. And then you get to poll a second time. The polling's open, so go ahead and discuss it. Bring the lights up, please. Bring up the audience lights, there we go. Yes. Oh, no, you don't talk to me about it. You have to talk to your neighbor about it. Yeah. I just started a 30-second timer, 30 seconds to wrap up your discussion and answer a second time. I expect more than 70% of you should have the right answer. Yeah, that's right. %7% of you now have the right answer. It's Galaxy B, of course. Because it has the longer period, it's more luminous. It's the lighthouse beacon. So therefore, if they both appear the same brightness, the one that's truly brighter has to be farther away. So that's why Galaxy B is farther away. Now, to make a editorial note, you come to these science cafes to hear how wonderful our college is in scientific research. It's wonderful. But we also are on the cutting edge of science education in the College of Science at the University of Arizona. It's not just me, a lot of us. You're going to see another one next month, Jessica Kapp, who does amazing things in the classroom. What studies have shown is that sitting, taking notes, and listening to me, no matter how interesting I may sound, that's too passive. You're not going to learn. I do this every 15 minutes, sometimes every 10 minutes in my class. My students do this with their clickers. You've always heard the old adage, the best way to learn something is when you have to teach it to someone else. My students who are getting it reinforce their understanding because they have to explain it to a classmate. And my students who are lost get to hear somebody else explain to them in different words than I would use. But the idea is and I also ban cell phone use in my class, so they don't have that distraction. You have to talk about the material in the classroom. And that is what makes the educational process better, I think, for the college students who take my core classes. And by the way, they're not all 18 and 19-year-olds. This semester I had one lady who was retired who took the class, and I had another gentleman who was an Army vet, 45 years old. So, we get those students too, but getting them to talk to each other makes them more active. When I do a physics demo, before I press the button or drop the ball, I make them predict what they think is going to happen with the clickers. You see, and by using clickers, you see, if I had you raise your hand, other people would be influenced by how you were voting, and you'd be influenced by how they were voting. This way, you don't know what everyone else is voting. You just know the end result. Someone had a question over here? Yes.
Brighter that means the mass of that has got to be expanding.
Yes.
The mass of the Earth were to expand 2 to 5%, it would cause extreme.
No, it's not the mass stuff. The thing that changes the brightness is the surface area of the star, which goes as radius squared. I'll talk to you after, since this lecture is about the Big Bang Theory, I don't want to get off topic about that, but I'll talk to you about it after the lecture. All right, this gentleman doesn't get enough credit. He was Hubble's partner in science, but Milton Humason never made it out of the 8th grade. He was a mule team driver, but he helped cart all the telescopes in the 1910s up to the Mount Wilson Observatory. And then he got a job there as a janitor because he thought the astronomy thing was cool. And then one night when the night assistant was sick, he took over because he was the janitor, he was there. Turns out he was better than anyone with a college degree learning how to use a That doesn't happen today. But in 1910, that could happen, you know. But what he did is he took spectra of all these galaxies that Edwin Hubble was finding Cepheid variables for, to measure distances. And he worked with Hubble, who measured the distances to these galaxies. There's something called the Doppler shift, and I don't have enough time to go into the details, but you've heard the Doppler shift in sound. If an object is emitting a wave, like a sound wave, and it's coming towards you, the pitch goes up. If it's light and the object's moving fast enough, the light gets bluer because it gets to a shorter wavelength. It's moving away from you, you see a longer wavelength than what is the wave that's emitted from the object. So what they did is they plotted the distance to every galaxy that Hubble found Cepheid variables for, and versus the velocity that Humason calculated. And they came up with Hubble's law. Very famous law, the other thing Hubble was famous for, and they named a space telescope after him. Velocity of a star, of a galaxy, is some constant times its distance. And here's what it looks like in graph form. I just looked at the clock, so I'm kind of moving along here. All right? This is a cute little thing from the online homework that my students use. You see the little observatory thing there moving around, right? And so you click on this galaxy. There's the picture of the galaxy. There's its distance. There's its velocity of recession. What Humason found was almost every galaxy that he saw showed that its absorption lines, these are colors in its spectrum. Astronomers are always studying rainbows, okay? But they don't see them as rainbows. They always digitize them. This is a rainbow. Every single point on the x-axis is a different color. It's a different wavelength of light. And some of the colors are missing and some of the colors are brighter. The colors that are missing are these, what are called these absorption lines. And what they would find is that every element has a certain fingerprint, a certain color that it emits or absorbs. And if they find the lines of calcium, for example, these are caused by the lines of calcium. In the laboratory, they're at a certain wavelength. But in these galaxies, they're at a longer wavelength. This is what's known as the redshift. And the more that shift is, the faster the galaxy is moving away from you. And so in this cute little thing, you know, when my students click a galaxy, they get the velocity at which the galaxy is moving away from us versus the distance. And what Hubble and Humason did was plot this on a graph where the x-axis is distance from the Milky Way and the y-axis is how fast it's moving away. And I think this is actual data from Hubble and Humason. So there were bigger inaccuracies in their measurements than we have today. But basically what you see is a line. That's Hubble's law. It's a linear relationship. Galaxies that are closer to the Milky Way move more slowly away from us than galaxies that are further away. The farther away a galaxy is, the faster it appears to move away from us. This was evidence that our universe is expanding. There it is, the Hubble's law. And this particular, astronomers spent decades trying to measure the exact value of this slope of this line, which is known as Hubble's constant, which we measure in weird units, just so that the numbers can be 2-digit. But anyways, and eventually now we think this number is 72, okay? In kilometers per second per million parsecs. But it turns out, and Einstein, in his equations of general relativity, which showed us that time isn't always constant, time runs at different rates for different observers, also predicted the universe should be expanding. But in 1915, they hadn't done this work yet. Einstein said, oh, that's silly. We know the universe isn't expanding. I'm going to have to add a constant that keeps the universe from expanding in all my equations. Then Hubble and Hummus in the late 1920s published this, and Einstein felt like a fool. He said it was the biggest mistake he ever made in his life, was creating the cosmological constant. He had predicted that the universe should be expanding. He should have had faith in his equations, because then he would have been even greater, lionized as a great genius when Hubble discovered that the universe was expanding. Turns out, though, we just learned, one of our former undergrad students, got his PhD at Harvard, won the Nobel Prize for Physics 4 years ago. First U of A graduate to win the Nobel Prize for discovering that the universe is actually accelerating and moving faster. And it turns out we need that constant that Einstein invented. So it turns out even when Albert Einstein thought he was wrong, turns out he was right. Okay, so I'm going to skip this because that's not important. I've got to get to the main article, what we're here to talk about, the Big Bang Theory, which is actually on right now on CBS. So if you DVR'd it, you could see it. Oh, you can see all the clips I get from that show to play in class. The first and simplest atoms were created in what we call the Big Bang, because if the universe appears to be expanding, that means it had to be expanding from somewhere. If it's getting bigger all the time, that means going back in time, it was smaller and smaller. So, and this wasn't always, thought of as an idea. In fact, the guy that first came up with what we know as the Big Bang Theory was a Catholic priest named George Lemaitre in the early 1930s, late 1920s. And the idea that the universe actually had a beginning in time, that you could say time t = 0. So I always get the question in class, what happened before the Big Bang? Well, you can't ask that question. There was no before, right? There was no time. Time began at the moment of the Big Bang. And that's also when the atoms were created. And in astrophysics, what we've learned is that more complex atoms are created in the stars. It's the stars. You've heard Carl Sagan. Most of you here, old enough to remember Carl Sagan. He called us all star stuff. Because after the Big Bang, the only matter that existed in the universe was hydrogen and helium. That's it. So all the other atoms and elements were cooked inside of stars. When a star dies, those new elements, carbon, nitrogen, oxygen, iron, silicon, I like to say it the British way, aluminium, okay, tin, gold, silver, they are expelled into space. So not only are stars element factories, they're excellent recycling plants. They recycle the elements into the galaxies so that new stars and planets can form from the newly formed heavy elements. And there's just a nice little, and again, this is the whole Carl Sagan thing. Most of the atoms in our bodies, except for the hydrogen that's in the water molecules in your body, were created in the cores of a star. I'm going to skip this because we're here to talk about time. How old is the universe? And there I'm going to go back to Carl Sagan again, and Neil deGrasse Tyson then picked up on it when he redid Cosmos. The cosmic calendar. Turns out our best estimate for when the Big Bang occurred was 13.8 billion years ago. So we live in a universe, again, we're measuring the year based on how long it takes our Earth to make one orbit around the sun. That's our unit of time. Given that unit of time, our universe has been around for 13.8 billion years. That's kind of hard to think of because when you get to big numbers, so instead, this was a great idea. I don't know if it was Carl Sagan's original idea. I like to think it was. We all live our lives by the calendar. We have a feel for the calendar. So let's imagine that the entire history of the universe was one calendar year. In that case, 1 month would be approximately 1 billion real years. Okay? And here's our beautiful cosmic calendar, where we have January 1st up here and December 31st down here. And here's some nice drawings of what looks like is going to happen. So if we consider that 13.8 billion years of the galaxy, of the universe, excuse me. And we shrink it down to 1 calendar year, then of course the Big Bang occurred on January 1st. Midnight, January 1st, Big Bang. The universe is now open for business. Then on July 22nd is when the first galaxies formed. January 22nd, first galaxies are forming. But that's not our Milky Way. When did the Milky Way galaxy form? On this cosmic calendar, the Milky Way doesn't form until March the 16th. So there isn't even a Milky Way for the first 2.5 months of our universe. The disk of the Milky Way, when the Milky Way first formed, it was a spherical configuration. And the oldest stars in our galaxies, those globular clusters that Harlow Shapley observed and analyzed, they were formed back on March the 16th. But the disk of the Milky Way, the rest of, as the Milky Way spun faster and faster, all of the loose gas flattened into a pizza pie shape. That's the disk of the Milky Way. That's where we live. That disk didn't form until May the 12th. What comes next? Nothing much happens over the summer. When does the sun form? Big Bang started on January the 1st. Our sun and Earth do not form until September 2nd. So right away, you can see that most of the universe happened before us. Us in a very loose sense, in the fact that there's an Earth here. Now, September 6th would correspond to the oldest rocks found on Earth. I'm sure Jessica can tell you more about that. The oldest rocks that we have found on Earth were formed in the cosmic calendar on September the 6th. On September 21st, the first life, and this is very crude life, not multicellular life, but the very first life arose on Earth on September the 21st. On October the 29th, we had the oxygenation of the atmosphere. This is when enough plankton in the oceans pumped up enough oxygen so that it stayed in the atmosphere. That's October 29th. December 20th is when we see the development of land plants. December 20th. December 25th, Christmas Day, is when the dinosaurs appear. December 25th is when the dinosaurs appear. December 30th is when the dinosaurs disappear. Okay? That event, probably an asteroid or comet impact that caused the death of most dinosaurs. I guess the flying dinosaurs became birds. That's what we're told now. That's December 30th on our cosmic calendar. We're Homo sapiens. Nowhere to be seen. Now, it's going to get very, very messy if I try and put a lot of text in that last little square. So on the next page, here's the cosmic calendar for December 31st. December 31st at 9 p.m. is when the early hominids appear, our earliest ancestors. Modern humans evolve at 11:58 p.m. on December 31st. Now, what about in that last minute, 11:59 p.m., there's one more minute left until today. At 11:59 and 35 seconds, agriculture arises. 11:59 and 49 seconds, the pyramids are built. 59 seconds, Kepler and Galileo prove Earth orbits the sun. So basically, all of human history fits in the last 15 seconds of the cosmic calendar. That really shows you something about time. We may think time is a long expanse. For us, we have just lived in a blink of an eye of the entire age of the universe. I also, you know what, I may not have time to talk about this, but I just wanted to mention this. The Big Bang Theory didn't really come into vogue until the 1960s and 70s. Back in the 1930s, there was a competing cosmology that was proposed by Sir Fred Hoyle, Theodore Bondi, and Tommy Gold, another professor at Cornell. It's called the steady state theory. In the steady state theory, the universe is not expanding. It's the galaxies are moving through it. They're just all moving away from us. And the universe is infinite in space and in time, meaning that the universe was always here. My personal belief is because many cosmologists, philosophers, astronomers were atheists, I think they liked the idea of having a universe that never had a beginning. Then you don't need a creator, right? That's just my personal opinion of why this appealed to so many astronomers in those days. But here's the problem. If this is true, we've got to be in a special place because all the galaxies are moving away from us. In an expanding universe, no matter what galaxy you're at, all the other galaxies appear to be moving away from you. So there's no special place. And also, there are still galaxies nearby us. So there had to be special places where new galaxies were manufactured, you know, to fill up the space around the Milky Way. So this was a problem with the steady state theory. Let's try a clicker question. Suppose that the universe is static and every object in it was created simultaneously. So we live in a steady state. The universe isn't expanding. And let's say every object, every galaxy, every star was just created simultaneously 13 billion years ago. Which of the following statements is true of an object which is 14 billion light years away? Oh, I made a mistake. So I'm going to make you, because we're not going to have time to discuss it, I'm going to have you poll again. I forgot I didn't have a timer on this one. So go ahead and answer it. Which of those statements is true? All the galaxies appeared 13 billion years ago. What can we say about a galaxy that's 14 billion light years away? Okay, I'm going to cut things off. We're not going to have time to discuss it because I'm running up against the clock. But look at this. 42% of you got the right answer, but there were a same number of you that thought you'd never be able to see it. Turns out light has a finite speed, finite time. So if an object's 14 billion light years away, it's going to take 14 billion years for the light from that galaxy to reach us. But if all the galaxies appeared only 13 billion years ago, there hasn't been enough time for that light to get to us. So we have to wait a billion years before we can see it. This is what leads to something astronomers call look-back time. That's why I mentioned in the promo for this that we astronomers have the ultimate time machine. When we look, because light has a finite speed, sure, light can orbit the Earth 7.5 times in 1 second. So for us, it seems instant. I press the button, there's the laser. But for an object that's billions of light years away, it takes billions of years for that light to get here. The farther out in time we look, the further back in time we're looking. And that's how we were able to learn these things. So the Big Bang Theory, universe itself is expanding, space may or may not be infinite. Turns out we now think it is infinite, but the Big Bang Theory didn't say it had to be. And time is not infinite, there was a beginning. All of space at one point. And here's the interesting thing. The age of the universe can be calculated. This is the reason why people wanted to know the value of Hubble's constant, the slope of that Hubble Law line, because the reciprocal of it is the age of the universe. But here's the problem. You know, astronomers are great with terminology that's misleading. Hubble's constant's not a constant. It changes with time. And so you have to factor that in trying to come up with the answer. Okay. This is one interesting thing. I'm going to jump around to 2 or 3 points before I call it out for questions. But this is kind of interesting. Everyone knows this equation, right? E equals mc squared. And today in astrophysics, it's a one-way street. This is what happens in the core of the sun. Matter is converted into energy. That's how the sun can shine for 10 billion years. Because when you convert a little bit of matter to energy, c squared is the speed of light squared. The speed of light's a big number. Speed of light squared is an even bigger number. Little bit of mass times a huge number gives you a huge amount of energy. So when we convert matter into energy, hydrogen turns into helium, some of the mass got converted into energy, we can generate a lot of energy. But at the moment of the Big Bang, E equals mc squared was a two-way street. Turns out energy could be turned into mass. If the temperature is more than 1 trillion degrees, and in the first few moments of the Big Bang, the universe was hotter than 1 trillion degrees. So what happens is 2 gamma ray photons, all the light, all the energy in the universe was in gamma rays, gamma radiation. If 2 photons of gamma radiation collide, they would form a proton, but they would also have to form something called an antiproton. Or they would form a neutron, and then they'd have to form an antineutron. An antiproton looks and smells and tastes like a proton, but it has a negative charge instead of a positive charge. Or it could create a negative electron and an object called a positron, which looks and tastes like an electron, but has a positive charge. This is what we call matter. That's what we call antimatter. So in the very beginning of the universe, energy was colliding to create matter and antimatter. When 2 identical particles of matter and antimatter collide, of course, they annihilate each other and form gamma photons. So energy was becoming matter and antimatter. Matter and antimatter was becoming energy. This leads to a problem in astrophysics and in the Big Bang Theory. If that's how it really happened, then why are we here? Because once the universe cooled down to where that couldn't happen anymore, all the matter should have found all the antimatter and destroyed it, and the universe would be one big universe of light. We wouldn't be here. Obviously, we're here. So either somehow more matter got created than antimatter, or they got segregated, which is even scarier, because one of those galaxies way out there could be made of antimatter, and we'd never want to come close to it. Okay, so what I want to do, I can't give you the details of this, so what I'm going to do is head over to make 1 or 2 more salient points. Why is it that we accept the Big Bang Theory? One is the object I started with. I'm not even going to go into PowerPoint mode. It turns out we are immersed in a sea of microwaves. That was discovered by accident by Penzias and Wilson, who were working for Bell Labs. And it's funny because I have to tell the 18-year-olds in my class, yes, there was only one phone company, right? There's just why we called her Ma Bell, okay? And Penzias and Wilson in 1966 were trying to develop cell phones. They were trying to develop wireless technology using microwaves. And they found this static everywhere, no matter where they looked. And they were pretty quickly able to rule out human-caused. This isn't human-caused. It's coming everywhere. And then a friend of a friend of a friend told them, you got to talk to these guys at Princeton. Turns out the Big Bang Theory predicted that in the first 300,000 years of the universe, it was so hot that all the hydrogen and helium was ionized. And so photons of light scatter off of electrons. And in fact, I think I've got a nice little animation to show you that, because this is a really good concept here. Here it is. Emission of the cosmic microwave background. What will happen is when the universe got down to a temperature, 3,000 degrees, see right now, everything's ionized. There's a proton, there's a helium nucleus, 2 protons, 2 neutrons, and all the little blue dots are electrons. And can you bring down the lights here on the stage? They don't need to, no, bring them down. I want them to see, I want them to see those little blue dots, okay? Notice that when the universe was too hot, it was opaque. Photons couldn't go very far. But once we got to 3,000 degrees, the electrons formed atoms of hydrogen and helium. Now the photons were free to travel through the universe. Okay, you can bring it up. So the universe became transparent. All that light that was emitted is still there. It was infrared at the time, but now the universe is expanded, so the wavelength of this light is expanded to microwaves, and it's everywhere. Big Bang Theory predicted it. The guys from Bell Labs found it by accident. That's one good thing. The other thing is the Big Bang Theory predicts the first 3 minutes of the universe, the entire universe was so hot, it was hotter than the core of the sun. It was one big nuclear reactor. It turned hydrogen into helium. According to the Big Bang Theory, there should be, for every here it is, for every it's a 3-to-1 ratio, right? 25% of all the matter should be helium, the other 75% hydrogen. That's pretty much the ratio we measure today. It's a 3-to-1 ratio between hydrogen and helium. Big Bang Theory predicted it, and turns out to be correct. So, I had one more clicker question, but we're not going to be able to do that. Eventually, our galaxy is created. Well, actually, this is an interesting thing too. This is so much interesting stuff. I wish we had a 2-hour lecture, but I know you wouldn't appreciate that. No. I'm not going to overstay my welcome. It's easier if I do it this way. Then I can see them all. Here we go. After that happened, as I said, about 300,000 years after the Big Bang. The universe became transparent. Then what happened is that there was a time before 1 billion years where the universe, it's the one before this, from 380,000 to about 1 billion years, the universe was filled with atomic gas, and there were no stars. And this radiation in the universe was infrared. Therefore, the entire universe was dark. We actually call it the cosmic dark ages. The cosmic dark ages from about 400,000 years after the Big Bang to about 1 billion years, which is when the first galaxies formed. Before the first stars formed, there was no light. There was no visible light. Just this infrared light that was permeating the universe. Those were the dark ages. But then when the first stars formed, we started forming galaxies. And then that was this other pretty picture that I was able to show you, and that is here. When a star forms, it's gravity. Gravity takes over and starts collapsing and collapsing and collapsing. And it can only do this if the gas is very cold, because that means the atoms and molecules in the gas don't move very fast. There isn't enough thermal pressure to overcome gravity. If you can quickly, under gravity, make the ball of gas get smaller, gravity goes up. Gravity gets stronger. It's a runaway effect. And even though the star heats up because of this, it can't generate enough pressure to stop the gravity. And eventually, the core of the ball becomes so hot that nuclear reactions occur. And what you get is a star. So, I am now going to switch to this wonderful animation that I want to show you. It's from the Illustris project. The Illustris project, it's a group of people at MIT and Harvard and France and Germany, and they use supercomputers at Harvard and I'm from Cornell. I'm sorry. I will never say it with respect. And what they've done is using all this supercomputer. Bring down the lights, please. You're going to bring down the lights on me, right? This is a supercomputer using the best knowledge of gas dynamics and gravity. This is what we think the universe looked like. First, let's go back. Let's start at the beginning again. We start in the cosmic dark ages. There's the cosmic dark, and I can do this on full dome. I did this in the planetarium. This is the cosmic dark ages. Now the first stars form. And notice they form in very clumpy areas. It's not uniform. Galaxies and stars form along these filaments. And where the filaments cross and crisscross, you have clusters of galaxies. But there are also whole volumes of the galaxies where there are, of the universe where there are no galaxies. We call these voids. So you can see this is from actual data, this computer simulation. And now the clusters and galaxies get really hot. You'll start to see some feedback from black holes that form in the center of these galaxies that send out bursts of energy that re-energize. But notice, this is how our universe is structured spatially. The galaxies lie along these filaments. It looks like a spider web. And where the filaments cross, you get these big clusters. And then there are whole volumes where there are no galaxies. So we have voids and we have clusters. And this is there, we have, up until the present day, all of these galaxies forming, looking like that. So, yeah. You can down, if you go to, just Google Illustris, I-L-L-U, S-T-R-I-S. You'll find their website. You can download. This is meant for full dome, but there's a, flat screen, easy MP4 video that you can download. So what and it really looks impressive on the planetarium dome. I was able to wow my students with that 2 weeks ago. So in the end, we actually see, here are examples from the Hubble Space Telescope that show us that our ideas of how planets form around stars are true. Here are debris disks around stars. We have to block out the light from the star, and we see in the infrared there are disks of material around other stars. This is what the planets form out of. And our Earth formed out of such a debris disk that was around the newly formed star called our sun about 4.6 billion years ago. So I guess my job today was to get you from the Big Bang, which is 13.8 billion years ago, to a time at about 4.6 billion years ago, or September in the cosmic calendar, where the Earth formed. Because next month, on January 14th, Jessica Kapp from our Department of Geosciences is going to tell you the story of geological time. Okay? And I have to quit. I'm sorry. It's it's 7:30, so, but I'll take, if you're willing to hang around, I'll answer any questions that I can. Yes?
We always hear about the expanding universe.
Yes.
What is it expanding into?
Tom, can you repeat the question?
Yes. We hear about the expanding universe. This gentleman wants to know, what is it expanding into? Well, don't forget, the universe is everything that exists. It's kind of like the question, what happened before the Big Bang? You can't ask that question because you're talking about non-existence. You can't have something outside our universe. So the universe is not expanding into anything. It's just expanding because it's everything that exists. And here's one of the problems that we have in trying to understand this. Einstein was able to build a mathematical model because in mathematics, you can create all sort of stuff, right? And we talk about dimensions. And Einstein worked in what we call space-time. He worked in a four-dimensional space. Well, in mathematics, that's easy. You have an x-axis, a y-axis, a z-axis. You can just add a t. You can add a fourth, and you can do the math. But we are three-dimensional creatures. It's hard for us to perceive that fourth dimension. We really don't perceive time because in the other three dimensions, we can go in both directions, not time. And what is a dimension? A dimension is something that is 90 degrees or perpendicular to any other dimension. So you've got forward, backward, there's one dimension. Then there's left and right. Okay, that's two dimensions, and there's 90 degrees to each other. Then there's up and down. That's 90 degrees to both of the X and Y, to up and down, and left and right, and forward, backward. So now the fourth dimension would be 90 degrees to all three of those. Think of the balloon that's blowing up. If you have a flat amoeba on it, it's a two-dimensional creature, right? It sees its two-dimensional universe expanding as the balloon blows up, but it doesn't perceive why it's expanding because it has no concept of up and down. We know that as we keep blowing up the balloon, the radius of the balloon increases. But the two-dimensional creature living on the flat surface of that balloon has no concept of the radius of the balloon. It has no concept of that third dimension. Likewise, we have no concept of that fourth dimension, which is expanding, that makes the three dimensions that we live in, that we perceive, expand. So that's, I think, part of the reason why the human brain, ask the psychology guy what he's talking in March about how the human brain perceives time. Ask him about how the human brain perceives dimensions as well, because that's one of the reasons why it's hard for us to think. We think that it has to be expanding into something. Well, it's expanding, I guess, into the fourth dimension, but we can't perceive that fourth dimension, which is time. Your question, sir.
Thank you. Great lecture.
Oh, thank you.
I got to take this. So the question is the role of
dark matter
Okay.
and dark energy
Mhm.
vis-a-vis from T0, Big Bang,
Right.
today, the relationship of the expanding universe and curiosity is dark matter seems in energy both tend to be a constant percentage of the universe, or is it itself expanding or declining? And
Right. As far as we can tell now, as best as we've been able to measure it, okay, it seems to be a constant percentage fraction, okay? But and this is hard because I don't do this for a living. So the dark energy thing, they just made up that name 20 years ago when it seemed like because of the work that our former our alumnus, right, who won the Nobel Prize, that the universe is actually expanding. So for those of you who don't know, dark matter, it turns out we know that matter, as Einstein showed us, warps the space-time around it, which is what we perceive as gravity. Newton had this sort of, this invisible force that attracts anything with matter to something else. The problem is there turns out to be matter in our universe that gravitationally attracts other matter, but it does not interact with the electromagnetic force, which is light. It doesn't emit light, it doesn't reflect light, it doesn't absorb light, so we can't see it. And it became evident when we studied these clusters of galaxies, like in that animation. And there was a guy named Fritz Zwicky who did his work back in the 1930s and 40s. And he discovered this, but nobody really believed him because he was a crabby old man and people didn't like him, And when you're a crabby old man, it's hard to get people to accept your ideas. And because human beings do science. But what he found is that when you look at the galaxies' motion, they can actually measure their Doppler shifts and how fast they're moving. Turns out that the motion, which is presumably caused by gravity, was greater than the gravity that could be generated by all the mass they could see and count up. It says the same thing with the rotation curve of our galaxy, okay? Because there is a supermassive black hole in the center of our galaxy, there's a large concentration of matter. Think of it this way. The sun is the most massive thing in our solar system. Which planet orbits fastest around the sun? Mercury. And then Venus a little less fast, and then Earth a little less. The planets that are farther away orbit more slowly. Turns out that if most of the mass in our galaxy is concentrated in that supermassive black hole, the stars near the center of the galaxy should move fastest around the galaxy. And that's true. We've measured some stars. My colleague Andrea Ghez, who was a postdoc with us, professor at UCLA, measured a star that takes 9 Earth years to go once around the center of the galaxy. Okay? Our sun takes 240 million years to go once around the galaxy. But as you go out and you measure the speed of stars orbiting the center of the Milky Way galaxy, they increase, okay, and then decrease, and then they flatten out. They flatten out. You would think that the stars that are at the very edge of the Milky Way are the ones that should be moving the slowest. But they aren't. They're moving faster than they should, which means there has to be some other gravity that's not generated by that supermassive black hole in the center of the Milky Way that is pushing them along. And so there appears to be a halo of matter around all these galaxies, but we can't see it. So we call it dark matter. So the game was, I had mentioned briefly when I showed you about the Big Bang saying that the universe could be open or closed or infinite or finite. That's because the Big Bang theory in itself didn't predict if the universe is infinite or finite. A finite universe would mean if I travel long enough in one direction, I'll come back to where I began. Just like on the two-dimensional surface of the Earth, if I could walk across water or take a boat, if I keep going in a straight line, I'll come back to where I began. Okay. It all had to do with how much matter is in the universe. That balloon blowing up, and the surface of the balloon is like the expansion of the universe, right? And the bicycle pump is that energy that's fueling the expansion of the universe. Let's imagine that we had galaxies. We could put little thumbtacks on the balloon, but they don't break the balloon. Each little thumbtack would be a galaxy. Now let's connect all those thumbtacks with rubber bands. Okay? As they pull away, the rubber bands want to pull them together. The rubber bands are like gravity. So while the universe is expanding, all of the galaxies in the universe are attracting each other. They're putting a brake on the expansion of the universe. So in cosmology, the key was always, what is the mass density of the universe? Because how much mass is in the universe? The more mass you have, the stronger the gravity between all that matter, and the stronger the braking force on the expansion of the universe. And so astronomers and cosmologists calculated something they called the critical mass density. That would be the critical mass density, the amount of matter you would need in the galaxy to generate a force of gravity that would perfectly balance the Big Bang expansion. So if we counted up less matter in the universe than the critical density, that means the universe would expand forever. It would slow down, but still keep expanding. If it was at the critical density, the universe would slow down and in the distant future stop. If you had more matter than the critical density, eventually the universe would stop. If it would break faster, stop expanding and then start contracting again, and we'd have a big crunch. And that was always when I took my cosmology class in graduate school, 1983, okay, that was a possibility. Since the discovery of the dark matter and trying to calculate it and count it, we counted all the visible matter. It turns out that when you even add the dark matter to the visible matter, it only accounts for a few percent of that critical mass. So there isn't enough mass in the universe that we can find to reach that critical mass. So that would tend to tell us that, okay, the universe is expanding. And it's going to keep expanding, but it should be slowing down. The problem is our alumnus, Brian Schmidt, and his colleagues. They found a way. I told you about the Cepheid variable, but that's not the only standard candle. There's another type of standard candle called a type 1a supernova. My textbook calls them white dwarf supernovae. It isn't a massive star blowing up and creating gold, which is what massive stars do. This is a type of supernova where a white dwarf, the white dwarf is the dead remnant of most stars, like our sun will die as a white dwarf one day. But the quantum mechanical forces that keep the dead star from collapsing under gravity into a black hole are only so strong. And a gentleman named Chandrasekhar calculated that a white dwarf cannot exist with more mass than 144% the mass of the sun, 1.44 solar masses. It's impossible to have a white dwarf with that mass. And if a white dwarf is all by its lonesome, it'll just cool off and get dark and you'll never see it again. But if it's in a binary system, the gravitational forces of that very compact dead white dwarf can pull matter off of a companion star. And if it does that, it can actually add matter to itself. The problem is when it reaches that magic limit, star blows up. Because it's a different type of physical law. They're called degenerate matter, and it's made of carbon. And the carbon fuses while it's degenerate, the whole star gets converted into energy, E equals mc squared. But the interesting thing is whenever this happens, it's always the same amount of mass being converted into energy. So when these supernovae, these white dwarf supernovae blow up, they always have the same luminosity. That makes them standard candles. Here's an astronomical object whose luminosity we know without knowing its distance. So if I catch one blowing up in another galaxy, excuse me, I have to watch my gesticulation, then I know how bright. It's 10 billion suns. When one of these white dwarfs blow, they get as bright as 10 billion times the luminosity of the sun. Luminosity of the sun is 390 yottawatts. A yottawatt is 10 to the 24 watts. That's one with 24 zeros. So 390 yottawatts, yeah, try finding that light bulb at Ace Hardware. 3.9 times 10 to the 26 watts times 10 billion, which is 10 to the 10, 3.9 times 10 to the 36 watts. That's the luminosity when these things blow. Here's the problem though. How do you know when the star is going to blow up? You have to be lucky to be looking at the galaxy right when it happens. Well, the odds tend out to be for a given night. A night is half a day, right? So 365 days in a year, half of that, your odds are like 1 in 700 or so that any given galaxy you look at, say for a few hours or all night long, say you're going to look at it all night long, 1 in 700 some. let's round it off. We're astronomers, 1 in 1,000. Okay, that you'll see a supernova. So you won't see one if you just point. How do you see them? You observe hundreds of thousands of galaxies every night. Then you're going to see hundreds of supernovae every night. But human beings can't work that fast. Robots and computers can. It's because of computer technology that we have all these robotic telescopes, and that's what Brian Schmidt was working on. All they do is bang, 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 bang. They look at hundreds of thousands of galaxies every night, and it would take a human being years to go through all the data, but a computer can do it just like that. And that's how he was able to more accurately find type 1 white dwarf supernovae and accurately measure the distances to these galaxies. And what he found, remember Hubble's law, distance to the galaxy goes as the velocity at which it's moving away from us. So at least with our understanding of Hubble's law for the galaxies nearby us, from the redshift of a galaxy, how fast it's moving away from us, we should be able to calculate its distance. He found with these white dwarf supernovae, these distant galaxies were even farther away than we thought for their redshift, for their velocity. Meaning that at very far distances, which is very far back in time, the Hubble law, that Hubble constant, which isn't a constant, is really different. And the only model it fit is a galaxy that's going to start accelerating. So not only is the galaxy going to, the universe, excuse me, is going to expand forever, it's going to expand forever at a faster rate, which means it's going to get bigger faster than we thought. And eventually one day, when all the matter in the universe is converted into stars and there are no new nebulae to make stars out of, and then the stars die and become neutron stars, black holes, dead white dwarfs, we're going to have, I think T.S. Eliot wrote that poem, How Will the Universe End? With a bang or a whimper? It's going to end like a whimper, okay? And so, so the bottom line is, why? Where's this energy? What's making the universe speed up? We see the result. What's the cause? We have no idea. But since we had dark matter already, they thought it was cute. Let's call it dark energy, okay? We have no idea what it is. Yes?
With the recent work that they've done with the Large Hadron Collider, finding the Higgs boson and the Higgs field, what's the connection between the Higgs field? I know it gives particles mass. Could it be variable, or could the Higgs field itself be different?
To be honest, I don't know. That's not something I'm up on or that I study a lot of. And so, and you know what? I think the people that study it, they don't know either. Who knows? You know, probably my understanding of the situation is probably studying in these large superconducting colliders and all that is a way to find out what these things like dark matter and dark energy are. Because we're not going to be able to observe it with our telescopes. The only thing is that we can try and set up an experiment with these colliders at the microscopic scale to find it out. By the way, as you're leaving, before I forget, if you would put your clicker in the plastic box that's in the back there, I'd appreciate it. Yes?
With the galaxies being farther away speeding up, would it indicate, since it's an inverse square law, that they're expanding from a center?
No, because the whole idea is that no matter where you're at, they all look like they're going away from you. So no, there is, and that's at least one thing that's kept philosophically stayed true throughout all the centuries of cosmology, is that there is no preferred center to the universe. Yeah. Okay, I've overstayed my welcome, I can see. So take care. Come back next month.
Thank you all very much. And if you would fill an evaluation in for us out on your way out, that'd be great. Thank you.